In the tech industry, engineers build artificial intelligence pipelines fed by massive oceans of data. Yet, in real-world, high-stakes environments, these same models regularly experience data cascades, wild, unpredictable failures that bring the whole system down. We see the exact same pattern in human learning. A student can practice a subject relentlessly, drilling flashcards and completing assignments, only to hit a sudden, impenetrable plateau where absolutely no new comprehension takes hold. On paper, both systems look perfect. The AI has processed billions of tokens, and the student has logged countless hours of study. The intake pipeline is vast and active, but feeding another terabyte of text to the model or assigning another 50 math problems to the student does nothing to fix the underlying crash. The system remains stuck. These twin failures point to a specific structural problem. The mathematical methods we rely on to judge the quality of our input data are broken. When scientists and educators evaluate their source materials, they typically use an additive checklist. Industry standards like Datasheets for Datasets or model cards score a corpus by grading individual criteria and combining them into an overall rating. This chart illustrates a hypothetical dataset measured across 3 pillars. It scores exceptionally well on 2 fronts. It is 95% recent and 95% relevant, but it contains a severe flaw. Corrupted contradictory labels leave it only 5% pure. Because the standard checklist averages these factors together, the severe errors are diluted. The math grants this compromised dataset a passing grade of roughly 65%. That passing grade is an illusion of safety. By allowing high scores in one category to mask a near-total failure in another, we are calculating the reality of data quality with the wrong logic. The observer-dependent theory of everything, or ODTOE, provides a framework to map exactly where this data blindness occurs. The central variable in this theory is a parameter called lambda. Lambda represents empirical reinforcement. It is the accumulated experience of confirmations, the raw material required to build any coherent belief. To evaluate the actual quality of a data source, lambda isolates 3 precise variables. The first is recency, which measures how fresh the data is, accounting for the exponential decay of information over time. The second is density. This calculates the strict signal-to-noise ratio, ensuring the information is directly relevant to the task at hand. The final variable is purity. True learning requires an absolute absence of errors, biases, and internal contradictions in the source material. This formula reveals the rule governing these variables. Lambda is calculated multiplicatively. If we run that same failing dataset through the formula, the 95% recency and 95% relevance are multiplied against the 5% purity. The score plummets to roughly 4%. The framework formalizes this as the weakest link theorem. When the math is multiplicative, a single near-zero variable drags the entire equation down toward 0. It doesn't matter how fresh the corpus is, or how well the retrieval system isolates relevant documents. Those high numbers are mathematically powerless to compensate for a poisoned purity variable. The formula operates exactly like physical tension on a steel chain. The structure snaps entirely at its weakest point, ignoring the surrounding links. When a high-stakes AI pipeline collapses in the real world, it is not an unpredictable accident. It is the strict mathematical consequence of a multiplicative system hitting a zero-value component. The modern AI industry has spent years attempting to solve performance issues by scaling up raw compute power and expanding model parameter counts. The mathematical reality dictates a different approach. Systematically cleaning existing datasets to increase purity yields a much higher effective gain in model coherence than throwing more servers at the problem. A fraction of contradictory training data permanently caps the potential of the system. Raw processing speed cannot overcome a mathematical collapse at the source. For high-stakes applications, defensive data purification becomes a strict prerequisite for survival, rather than optional optimization. This math governs human education as well. We can finally answer why that relentlessly studying student hit an impenetrable wall. The root cause of their plateau is a curriculum misaligned with their current capacity. In the framework's terms, this is a collapse in the density variable. The signal-to-noise ratio has flatlined. This requirement for high-density information maps onto Vygotsky's foundational pedagogical concept, the zone of proximal development. Tasks outside this zone are entirely noise to the learner. The multiplicative formula proves why assigning more of the wrong homework cannot rescue a failing student. Drilling flashcards only increases recency, but multiplying by a near zero density still equals zero. The structural alignment must be fixed first. Mastering information coherence is a universal, fundamental law that strictly governs the intake of reality for any observer. Whether you are training a multi-billion parameter neural network or guiding a single human mind, absolute coherence relies entirely on the structural integrity of the source. Any intelligence is exactly as strong as its weakest link.